Okay, today we are going to study branching processes, which is something like this. It's best illustrated by an example. First, there is one individual, and this individual can produce certain number of offsprings, and this number of offsprings is a random variable. So let's say it produces three offsprings, and then this individual is eliminated from the population. Okay. So let's call this generation 0, and the generation of these offsprings is generation 1. Okay. And now each of these offsprings can produce offsprings. So with the same probability distribution as its parents. Okay, so let's say the first offspring can produces two offsprings. The second individual may produce one offspring, and the third can produce uh, two offsprings, and so on. So that makes the second generation. And the first generation individuals are eliminated from population. Now we consider the number of population at each generation, and that will be a random variable. So in the first population, zeroth population, generation population, that will be x0, which is usually set to 1 as an initial condition. And the population size of the first generation is x2, x1. In this particular example, it will be 3. And the number of individuals in the second generation is x2. In this particular example, there are 1, 2, 3, 4, 5 individuals, and so on. So this process goes on. And sometimes individual may not produce any offsprings at all. So if sufficiently many individuals do not produce any offsprings, then the population size may decrease, and eventually it can go extinct. So this is the branching process, because as you can see, they repeat branching, so it makes a kind of trees like structure. And this is similar to the birth and death process, but unlike the birth process, uh, each individual can produce offsprings at a certain, in a discrete time steps. Not in the birth process, individuals can produce offsprings at any time, right? But it's different here. So the generations are discrete. So first generation, second generation, and third generation, and so on. Now let's consider the problem of generational growth. So that means how the population size grows. So first we make some assumptions, and each individual produces a certain number of offsprings, and this is a stochastic phenomenon, but we assume that the probability distribution of the number of offsprings is known. So every individual produces offsprings. So let's say j offsprings. So j can be either 0, 1, 2, and so on. It's a non-negative integers. So j offsprings is produced with probability pj. Okay, so we assume this is known. So j is from 0, 1, 2, and so on. So the probability generating function is defined to be g of s, and j from 0 to infinity, and pj, and s to the power of j. And we assume x0 is 1. So we start from a single individual. Okay. Then in this figure, the generation 1 has 4 individuals. So there are 4 offsprings, so which was produced with probability P4. And then each individual in the first generation may or may not produce some offsprings. So in this example, this individual, let's say this individual produces 1, 2, 3, 4 offsprings, and the second produces only one offspring, and the third one does not produce anything, and the fourth one produces 2 offsprings, and so on. So the number of individuals in the second generation can be expressed as this. So we have x1 number of individuals in the first generation, and the second generation. In the second generation, we can express this number as this. Y1 is the number of offsprings produced from the first individual in the first generation, plus Y2, which is the number of offsprings produced by the second individual in the first generation, and so on. So we add this random variable up to y x1. So x1 is the number of individuals in the first generation. So this the very number of terms in this expression is a random variable, that is x1. So given this, for example, in the previous figure, let's see, this one. If you look at the second generation, y1 would be 4, and y2 would be 1, and y3 would be 0, and y4 would be 2. So the sum of these will be the number of individuals in the second generation. That's 4 plus 1 plus 2. That is 7. Now we have the following probabilities. First of all, probability that yk is equal to j is given by pj, because yk is the number of offsprings produced by a single individual. So that probability distribution is known. That is pj. And probability that the number of individuals in the first generation is equal to m is given by this conditional probability. So that is x1 is equal to m, given that x0 is equal to 1, which is, again, since x0 is only one individual, it's just 1, so it is same as pm. So this is the probability generation of the number of offsprings produced by a single individual. So it's the same pm. No, this one is pj, and they come from the same distribution. And of course, we also assume that we start from a single individual in generation 0. So x0 equal to 1 is, this probability is 1. Okay, so we know this information. And let's define this quantity hn, that is the probability that the number of individuals in the second generation is n. Okay, so this is the definition, and we want to find this probability distribution. So this is equal to, by using the partition theorem, let's say r is 0, infinity. So this r is the number of individual in the first generation. Okay, x2 equal to n given x1 is r times probability of x1 being equal to r. So this is application of the partition theorem. And as we have seen, this part is this. So that is P R, lowercase pr, and probability that xn equal to n, x2 equal to n given x1 is r. Okay, so let's calculate the probability generating function of this. So multiply both sides by s to the power of n and sum over n. So that probability generating function we call g2. So that is defined by this, and from 0 to infinity hn to times s to the power of n, that is equal to let's see, r from 0 to infinity pr and sum n from 0 to infinity, and this probability x2 equal to n given x1 is r times s to the power of n. So far this is just based on the definition. So how do we calculate this part? Okay, so let's see. This part is actually conditional expectation value of s to the power of n, right? So let's see. So this is probability x2 equal to n given x1 is equal to r s to the power of n. Okay, this is the expectation value of s to the power of x2 given that x1 is equal to r. Okay, but when the number of individuals in the first generation is r, then we know that x2 can be expressed as y1 plus y2 plus and so on up to yr, right? So we apply this. So we replace x2 by this summation of y's. Okay, so this expectation becomes s to the power of y1 plus y2 plus up to yr. So this given condition is actually incorporated in the number of terms in this sum. So now this is not a conditional expectation. And since this is exponential, we can split this exponential into the product of powers of s to the power of yr. And now each individual in the first generation produces offsprings independently of each other, right? So the expectation value of a product can be expressed as the product of expectation value. So this is equal to exponential of s to the power of y1 times expectation value of s to the power of y2 times and so on and yr. But this y1, y2 up to yr, they are independent and identically distributed. So, and also, each of these yi's is the number of offsprings produced by a single individual. So we know that probability distribution. And this expectation value here, each of these is nothing but the probability generating function we defined for the first generation. So this is equal to g of s, and g of s. So all of them have the same functional form. So r times. So that is g of s to the power of r. So that is this part. This part. Okay. So now, after all, the probability generating function of x2 is given by this. So summation r from 0 to infinity pr and g of s to the power of r. Okay, but now look at this. If you replace this term by simple s, then it will be the probability generating function of x1, right? So that means this is actually the composition of g with itself. Right? If you apply the definition of this g, which was g of s, by the way, was pr s to the power of r, right? R from 0 to infinity. And this s is replaced with g of s. Then we have this function. So g2 is actually the functional composition of g with itself. And if you continue this argument, before that, we also know g of 1 is 1. So g of 1 is equal to g of 1, which is equal to 1. Right? By the way, this comes from the normalization condition for the probability mass function. So anyway, so if we continue this argument, then we can see that g3, that is the probability generating function for the number of individuals in the third generation, is given by g of s. So that's this and this. And this can continue forever. And in general, the generating function for the number of individuals in the mth generation is given by this g of, and so on, and g of s, and something like this. So this is a composition of g with itself, and that composition is applied m times. So this is the general form of the probability generating function for the number of individuals in any generation. Now that we have the probability generating function, we should be able to calculate the mean and variance of the population size of any generation. In general, we have this formula for calculating the mean and variance using the probability generating function. So the mean is given by the first derivative, and s is substituted with 1, and the variance, so variance is given by using the second derivative and the mean. So these are just the general formula involving the generating function. So first, recall that G1, G1 is just G by definition. Okay, then let's try to find mu2, that is the mean population size of the second generation. So that should be given by this derivative, G2, and evaluated at 1. Okay, but G2 was the functional composition of G with itself. Okay, and so by using the chain rule, we have G prime 1 and G prime 1. So that is mu1 squared. Okay. Of course, G prime of 1 is mu1, right? So that's the mean of the population size of the first generation. And this is, of course, readily calculated because we know the probability mass function for this. So just apply the definition and we know the value of mu1. So mu2 is nothing but mu1 squared. In general, mu(n) is given by this. So it's the derivative of Gn, it's S, evaluated at 1. But Gn is G of Gn minus 1. Okay, so applying the chain rule, we have G prime 1 times Gn minus 1 prime of 1. Okay, so that will be mu1 times mu n minus 1, because the value of Gn minus 1 prime here will give us this mean value. Okay, so we have this recursive equation. To summarize, we have mu n is equal to mu1 times mu n minus 1. So if we continue this, then mu1 mu n minus 1 would be mu1 times mu n minus 2, and so on. So if we continue this, it turns out that mu n is equal to mu1 to the power of n. Very easy. Next, we want to find the variance. For that, we need to calculate the second derivative of the generating function. So let's see. The first derivative is by the chain rule. That will be G prime of Gn minus 1 of S times Gn minus 1 prime. And the second derivative would be, let's see. So that would be G double prime Gn minus 1 of S times Gn minus 1 prime squared, and plus G prime Gn minus 1 S Gn minus 1 double prime of S. Then we put S equal to 1, and remember gn minus 1 of 1 is 1. Okay, so gn double prime of 1 is g double prime 1, and gn minus 1 prime of 1 plus g prime of 1 and g double prime n minus 1 of 1. Okay, so let's see. And okay, and this one, g prime, gn minus 1 prime, this is equal to mu wait a minute, this should be equal to mu n minus 1, and this should be equal to, let's see, mu 1. And this part, g double prime 1, from the previous formula, wait a minute, where is it? From this one, this one. So when n is 1, we have g double prime 1 is equal to sigma squared, sigma 1 squared minus mu 1 plus mu 1 squared. So we replace this into here. We should have, let's see, sigma 1 squared minus mu 1 plus mu 1 squared, and we've seen before this one, mu n minus 1 is equal to mu 1 to the power of n minus 1. Wait a minute, so this should be squared here. So this one times mu 1 to the power of 2n minus 2 plus mu 1, so this is mu 1, and g n minus 1 double prime 1. Okay, so these values are all known, and what's unknown are this and this here. So if we put, let's see, un equals to gn double prime of 1, then we have a recursive equation. That is, let's see, so we move this one to the left, un minus mu 1 un minus 1 equal to this part. So that's sigma 1 squared minus mu 1 plus mu 1 squared times mu 1 to the power of 2n minus 2. So this is a first order inhomogeneous, because of this term on the right hand side, inhomogeneous difference equation. And to solve a inhomogeneous difference equation, we first solve its corresponding homogeneous case. So that would be un minus mu 1 un minus 1 equal to 0. So to solve this, we have to distinguish two cases. Okay, case 1, when mu 1 is not equal to 1. Okay, in this case, the general solution for this homogeneous difference equation would be this: un equals to some constant times mu 1 to the power of n. Okay, it's very easy to see that this is indeed a solution to this difference equation. Okay, and now to solve this inhomogeneous case, let's see. We have n here, So let's try some, we need to find some special solution. So that would be, let's say, okay, so this is homogeneous. And for the inhomogeneous case, let's see, it's constant times mu 1 to the power of 2n. So how does it work out? So if we substitute this into this equation, let's see, we have c mu 1 to the power of 2n minus mu 1 c mu 1 to the power of 2n minus 2 equals to, let's see, sigma 1 mu 1 mu 1 squared mu 1 2n minus 2. So this would be satisfied if let's see, so c mu 1 2n minus 1 mu 1 minus 1 equals to this. So c is equal to sigma 1 squared mu 1 squared, and these will cancel except for 1 over mu. So that would be what? Mu 1 minus 1. So if the value of c is this, then we have a special solution, that is un is equal to this c squared mu 1 minus 1 and wait a minute, what was it? Mu 1 to the power of 2n. So this is a special solution. So by combining with the solution for the homogeneous case, we have let's see, plus some constant times mu 1 to the power of n. Okay, and this constant b can be determined from the initial condition. That is the case for n equal to 1. So in this case, let's see, u1 should be equal to this. Now this comes from the original definition of the second derivative of the generating function for the for n equal to 1. So this, and by comparing this with this when n is equal to 1, then we should have b should be equal to, let's see, this. mu1 minus 1. So after combining, putting this b into here, the general solution becomes this. That is sigma 1 squared minus mu 1 plus mu 1 squared mu 1 mu1 minus 1, mu1 to the power of n, and mu1 n minus 1. So this is the general solution. So after all, sigma n squared, that is the variance of the population size, is un plus mu1 to the power of n minus u1 to the power of 2n. So substitute this, and after some calculation we have sigma 1 squared mu1 to the power of n minus 1 mu1 n minus 1 over mu 1 minus 1. So that's the variance for the case where mu1 is not equal to 1. Okay, next we consider the case where mu1 is equal to 1. So mu1 is equal to 1. In this case, the original recurrence equation, difference equation becomes this, un minus un minus 1 is equal to sigma 1 squared. But this is just an arithmetic progression. So it's easy to find the general solution for this. That is n times sigma 1 squared plus some constant. And this constant can be determined from n equal to 1. So u1 should be sigma 1 squared. And so therefore a is just 0. And in general, we just have sigma n squared equals to gn double prime of 1, which is equal to n sigma 1 squared. So it's just n times the variance of the first generation. So that's very easy. Let's summarize the results so far. So we have for the average population size this relationship. So on average, the population grows or shrinks exponentially. So if mu1 is greater than 1, then the population will grow exponentially. And if mu1 is less than 1, it will shrink. And eventually it will go extinct. And for the variance, it should be sigma n squared. For the variance, we have two different scenarios. If mu1 is not equal to 1, so that means the average number of offspring is not equal to 1, not exactly equal to 1, then the variance grows or shrinks exponentially, like this one. And if mu1 is exactly equal to 1, then the variance only grows linearly. Next, we want to calculate the probability of extinction, which means the population size becomes exactly 0. And this probability of extinction can be calculated as the value of the probability generating function at s equal to 0. Okay, this is because by definition, so this is j from 0 to infinity, and the probability, how should I write? Okay, probability of x n equal to j s to the power of j is like this, from 0 and PR 1 s and PR x n 2 s squared and so on. So if we put s equal to 0, then every term will disappear except for the first one. So s to the power of 0 is 1, so only this part remains. So when s is equal to 0, it is equal to the probability of extinction. Okay, so that's what we want to calculate. So to do that, let's define Gn as the value of the generating function at 0. Okay, and first of all, G1 of S is of course this, and we know the probability mass function for the first generation. This is given. So lowercase g1 is g1 of 0, that is p0. Okay, so this value is known. And from a previous result, we know that Gn of S is equal to G of Gn minus 1 of S. So therefore, lowercase gn is equal to this. G of Gn minus 1 of 0, that is G of lowercase gn minus 1. So hopefully, by exploiting the properties of this function g, we may be able to find these probabilities of extinction. So let's study those properties. So first of all, we limit the range of s to be in this interval from 0 to 1. And of course, pj's are always between 0 and 1 because it is a probability. So first property is that g of 1 is 1. So this comes from the normalization of probability mass function. And second, property 1 is that g of s is always positive as long as p0 is positive. So because s is always non-negative, so and probability is always non-negative, so adding to p0 any positive numbers results in a positive number. So this makes sense. And also, if you differentiate this function g, then it is again non-negative. So because the result of differentiation is this. So everything is positive here, so it must be positive, or at least non-negative. This means this function g is an increasing function. And if we differentiate again to obtain the second derivative, then it is again a non-negative function. So this means this function is a convex function. So together, this property 0 means if you draw a graph of this function on S with S as the horizontal axis and g of S as the vertical axis, it passes through this point 1, 1, right? 1, 1, and it is non-decreasing, so it's like increasing function, and it's convex function. Okay, so convex means like this, not like this. Okay, so more generally, a convex function means that the functional value is always greater than or equal to the tangent line at any point. Okay, so let's say if you draw a tangent line at this point, say, so tangent line is like this, and the points on the curve g of s is always above this tangent line. So this happens for any point. as long as the function is convex. Okay, so in general, you should prove this property. If a function f is convex, then we have the following property. If y is greater than x, then f of y minus f of x divided by y minus x is greater than or equal to f prime of x. So this is a general property of a convex function, which we will exploit later. So, as we have explained before, Gn of S is G of Gn minus 1 of S. So in particular, we have lowercase g2, which is g2 of 0, is g of g1. Okay? But this is, by definition, this summation. J from 0 to infinity, pj, and g1 to the power of j, which is, of course, greater than p0, because p0 is actually one of the terms on this in this summation. So, but p0 is actually g1 itself. So in particular, we have this. G2 is greater than G1. Okay, so this is one fact. Then we know that this function g is convex. So therefore, we have in particular this g of gn minus g of gn minus 1 and gn minus gn minus 1 is, this is equal to gn plus 1 minus gn over gn minus 1, which is greater than the derivative of g evaluated at gn minus 1. But this derivative is always non-negative. Okay. So, as long as if gn, so this denominator is positive, if this is the case, then gn plus 1 is also greater than gn. Right? So this means, and we do know g2 is indeed greater than g1. So if we continue this logic, this inference for g3 and g4 and so on, we see that this sequence of gn's, this is an increasing sequence, or at least non-decreasing. Is it non-decreasing? Decreasing. Increasing. It's increasing. And also, this is bounded because this is a probability, so it is always less than or equal to 1. So from calculus, you should know that bounded increasing sequence always converges. Right? So there exists this limit. Limit n approaches infinity, gn converges to some value. Okay, and since we have gn equals to g and gn minus 1, so if we move n to infinity, we should have this limit should satisfy this functional equation. So lowercase g is equal to uppercase g of lowercase g. So by solving this equation for g, we can calculate the probability of eventual extinction. Okay, we are not able to calculate this probability of extinction for each n, but we may be able to calculate the probability of eventual extinction. So that is when n is sufficiently large, then this will be the probability of extinction. There is a very simple algorithm for solving this equation numerically. That is just give some initial guess of this g and substitute this into this function g, uppercase g. Then define this as the next value, the next estimate of g. Then we use this value to determine the next value. And we continue this process over and over until this converges. So in other words, we are trying to find a fixed point of this function g. So fixed point means if we plug in this solution, then this function returns the same value as its argument. So in this case, we say g is a fixed point of this function g. Graphically, we can interpret this process as the following. So if we plot this function g, it looks like this, as we have explained. So it passes through this function point 1, 1. So this is 1 and this is 1. So draw a line connecting the origin and the point 1, 1. So this line is, so if we take this x-axis and y-axis, so we have one curve g of x and y equals to x. So this is the second one is this straight line here, this straight line, this one. So what we are trying to do is to find the point where this line and the curve crosses. So there are at least 2 points, this one and this one. Okay, but we are actually trying to find this one. So first, suppose we have g0 somewhere here, g0. Then we substitute this in, we put this value into this function uppercase g. Then using this function, we find, we draw a horizontal line to find the next value. So at this point is, so this y coordinate is g1. So this will be g1, g1. Okay. Then we substitute this g1 into this function again. That will be, so that will give you the value of g2. Then we draw the horizontal line again. So this point will be g2, g2. Then we put this value into this curve again, and we continue this until we reach this crossing point. There we have found this fixed point. After this point, this process doesn't move any points. Okay, what if we start from here, somewhere here? Then we will have this value first, then draw the horizontal line. The next value will be this. Next value will be this. So either way, we will reach this fixed point here. So that's what we are doing, to find the fixed point, and this will give us the probability of extinction, eventual extinction. Next, let us introduce the notion of martingales. So to do that, consider the following conditional expectation. that is the expectation value of xn plus 1, that is the population size of the generation n plus 1, given the past history. So x0, x1, x2, and so on up to xn. Of course, in the case of the branching process we are considering, this is a Markov process, so it doesn't really depend on this history except for the very last step, this one. But anyway, let us consider this. So this would be by a straightforward argument, it will be equal to xn times mu1, because each of the individuals in the nth generation, we expect mu1 offsprings. So after all, the expectation value, the conditional expectation value, given there are xn individuals here, then we expect this number of individuals in the generation n plus 1. Okay, now let's define a new random variable zn by this xn divided by mu n. So we divide the number of individuals by the expected number of individuals in the nth generation. So in this case, we know that mu n is equal to mu1 to the power of n. Okay, so let's substitute this into the previous equation. Then we have zn times mu1 to the power of n plus 1, given all the history, and zn times mu1 to the power of n plus 1, because we have extra mu1 here. So this mu1 to the power of x n plus 1 cancels out. So we have, after all, zn plus 1 is here, and xn equals to zn. Okay, so this means the conditional, so if we consider the sequence of random variables z1, z2, and so on, zn, zn plus 1, and so on. So if we consider the sequence of random variables, the expectation, conditional expectation value of this zn plus 1 is the same as zn. So in a sense, so the random variable doesn't change in a sense. So if this holds, then we say this sequence is a martingale. So that's martingale. This name comes from a strategy in gambling. So consider some gambling like coin toss. So first a gambler bets $1. Then in the next game, whether he wins or not, he bets $2. And in the next game, whether he wins or not, he bets $4. So every time he plays a bet, he doubles his stake, his bet. So this is called Martingale strategy. So here's a graphical representation of the Martingale strategy. In the first bet, the gambler bets $1. If he wins, then his stake becomes $2. And then in the next bet, he bets $2. If he wins, that will be $4. If he loses, he's broke. Not broke, but he's got $0. And in the first game, if he loses, he's got $0. Then he bets, in spite of being broke, he bets $2, for example, by borrowing money or something. If he wins, then he wins $2 because he bets $2, right? So if he loses, then he's now has negative $2, but this means he's in debt. But in the next game, he bets $4. So that means if he wins, now he has $2, right? And if he loses, that becomes negative $6. So his debts increases. But anyway, this is the Martingale strategy, and actually this is known as a sure way to win. Okay, it sounds strange, but the expectation value of the stake at any point is positive. To see this, consider he wins for the first time in the nth game. Okay, so this means he lost the first game, and he lost the second game, he lost the third game, until nth game. Okay, so that means in the first game he lost $1. In the second game he lost $2. In the third game he lost $4, and he kept losing until n minus 1th game. So that will be 2 to the power of n minus 1. And that is equal to 2 to the power of n minus $1. So now he has this much debt. But in the next game, he bets 2 to the power of n dollars. And if he wins, then he gets this amount of money. And that will, with this money, he can pay the debt and still have $1 left, right? So this minus this debt is equal to $1. So if he gets out now, he go home with $1 extra. So in a sense, this is a sure way to win. But of course, it requires lots of money, and you may end up in debt for a long time. So it's not recommended for obvious reasons. But anyway, this is the Martingale strategy. Now let us examine if this strategy is actually forming the Martingale in the mathematical sense. So we set random variables z0, z1, z2, z3, and so on as the amount of bet. Okay, so z0 is a random variable that can take the value 1 only. So this is only one value is possible. And z1 is a random variable that can take two values, 2 or 0. So those are the possible values of the bet in the second game. And z2 can take, it's a random variable that can take the values 4, 0, 2, and negative 2. And in a similar manner, z3 is a random variable that can take values 8, 0, 4, negative 4, 6, negative 2, 2, negative 6, and so on. Okay, so let's write it down. So z0 is a random variable that can take only 1. And z1 is a random variable that can take 0 or 2. z2 can take negative 2, 0, 2, 4. And z3 can take negative 6, negative 4, negative 2, 0, 4, 6, 8. So as you can see, these are okay. This can vary from some negative values to some large positive values, and in general, uh, we can write this set as this: Zn varies from negative 2 to the power of n plus 2 and negative 2 to the power of n plus 4 up to the power of n minus 2 and 2 to the power of n. So in case of Z3, the largest value is 2 to the power of 3. In the case of Z2, the largest value is 2 to the power of 2. And in case of 0, that's 1, 2 to the power of 0. Okay. And more generally, we can express this same thing as this. So it's of the form negative 2 to the power of n plus 2m plus 2, where m is 0, 1, 2, up to the power of n minus 1. Okay, you should check that for these values of m, we can recover this set of numbers, Okay. And any of these values, okay, appear only once in this set, of course, as you can see in this. Okay, so no two numbers are the same. If you can see, you can also check in here. Okay, so in each column here, every value is different from other values. So we can assume that each appear with the same probability. Okay, and that will be 1 over 2 to the power of n. So each of these numbers, so there are this many numbers, right? So 0 to 2 to the power of n minus 1. So there are 2 to the power of n numbers here. So each of them appears with the same probability, so that will be this. Now we can calculate the expectation value, unconditional one, of Gn. So that would be m from 0 to 2 to the power of n minus 1, and the probability of each number is this, and the value of each possible value of this random variable is to this. And if you calculate this, this will be equal to 1. So that's what we have seen in a previous example. No. Next, let us see some examples of the conditional expectation. Say Zn Z2 given Z0 and Z1. So we should enumerate all the possibilities of this history. Okay, so if you look at this diagram, Z0 and Z1, there are two paths. Okay, this and this. So the first one, let's pick this one. So Z0 is 1 and Z1 is 2. So given that, the expectation is calculated as this. So Z0 is 1 and Z1 is 2. So in this case, there are two possibilities, 4 and 0. Okay, two possibilities for Z2. Okay, so this expectation is 4. So Z2 can take the value of 4, with the probability 1/2. Okay, so this can happen with 1/2 probability 1/2 and probability 1/2, or 0 times 1/2. So that is 2. And the other possibility is z0, z1 is equal to 1 and 0. Okay, so that is 1 and 0. And each of these, okay, and for this, the possible values for z2 is z2 are 2 and -2. Okay, so 2, that happens with probability 1/2, and -2, which happens with probability 1/2. And the result is 0. And these two are the only possibilities for z2. So the possible values of this expectation, conditional expectation, is given as this 2 and 0. So 0 and 2. Okay, remember, conditional expectation is a random variable. Okay, so therefore this set means the possible values of this random variable, which is an conditional expectation value. And similarly, we can compute the conditional expectation of z3 given z0, z1, and z2. So applying the same technique, you should have 4, 2, 0, and -2. And okay, in either case, okay, so for example, in the case of this one, conditional expectation of z2, this set is actually the same as z1. Okay, so that's 2 and 0. Okay, so this is actually equals to z1. And in the case of z3, this is actually equal to z2, as you can see here. 4, 0, 2, -2. 4, 0, 2, -2. So in general, we can show for this system of gambling this expectation, conditional expectation, zn plus 1 given z0 up to zn is actually the same as zn. Therefore, this sequence of random variables, the amount of bet is a martingale. Now let's try to prove the martingale property for this system in general. So if you look at each step, let's say this step, the gambler can win or lose with equal probability, and at each step, let's say nth step, the next bet size will be 2 to the power of n. Okay, so in this case n is 1, so the bet size will be 2. And if he wins, then his stake will increase to 4, and if he loses, his stake will decrease by this amount. So let's formulate this in general. The expectation value of zn plus 1 given any sequence of z up to zn. Actually, it only depends on the last step, only on this step. So with probability 1/2, he can win, and the stake will increase by this amount, right? So currently he has this much money, and he bets this much amount of money, and if he wins, his stake will be the sum of these. Or he can lose with the same probability, and at that point his stake will decrease by this amount. Okay, so actually this is a Markov process because property because this expectation value does not depend on any of these, but only the last step. So after all, this is equal to Zn. So therefore, this sequence of random variables, Zn, is a martingale. And let's see a few more examples of martingales. So consider a symmetric random walk where so this is the a random variable, and with probability 1/2, it can increase to increase by 1. So xn may be xn plus 1, or with the same probability, xn plus 1 can be xn minus 1. So in this case, so this is the same random walk as we have seen in a previous chapter where we dealt with gambler's ruin problem. So in this case, this sequence of random variables is a martingale. So we can show this is of course a Markov process, and we can show that this is equal to 1/2 and times xn plus 1 or xn minus 1. So the result is xn. Therefore, it's a martingale. Next, consider the same random walk problem, but we define a new random variable by yn equals to xn squared minus n. Then this is a martingale with respect to xn. So that means conditional expectation of yn given yn plus 1 given xn is a martingale. So that is this. Okay, let's show this. So this one, the left hand side is by definition is this. So the conditional expectation will be 1/2, and xn will be increased by 1 with this probability. So the value of yn plus 1 would be xn, let's see, xn plus 1 squared minus n plus 1. Or, with the same probability, it will be xn minus 1 squared minus n plus 1. So if you expand this, we have xn squared plus 2xn, and 1 from here will be cancelled by 1 from here, so it will be minus n. And the next term is and minus n. So this will be cancelled by this, and we have the same thing here and here, but multiplied by 1/2. So we have in the end x squared minus n, which is yn. Therefore, we have a martingale here. We will be using this result in a later example. And that is the problem of stopping rule. So in general, let's consider a sequence of random variables, xr, where r is 0, 1, 2, and so on. So we want to stop this process once certain conditions are met. For example, we want to stop at a specific time, that is some given time t, we just stop. And in that case, we want to calculate, for example, the expectation value of this random variable x at time t. And second, we want to stop if the value of xr becomes greater than or equal to a certain threshold. Okay, stop if some condition is met. This condition is met. So this is the problem of first passage time. So what we want to know is the expectation value of this time t. Okay, so this time t is the time where this condition is met. So maybe I should write this as t. Okay, for the first time, x crosses this value. So what is this time on average? So that is the value of interest. Regarding this problem of stopping time, we have the following theorem, which we do not prove. Okay, let's call this stopping theorem. Let's say we have a sequence of random variables, which is a martingale. With respect to another sequence of random variables. Okay, so this means the expectation value of zn plus 1 given x0, x1, and so on up to xn is equal to zn. Okay, and let t be the stopping time. Stopping time. And also we impose the following three conditions. One, the probability that t is finite is 1. So almost surely the stopping time is finite. And 2, the expectation value of the modulus of zt is finite. And 3, expectation value, conditional expectation value that of zn given t is greater than n, a certain number, times probability that t is greater than n converges to 0 as n goes to infinity. Okay, then we have unconditional expectation of zt is equal to unconditional expectation of z0. So this is the theorem. As an application of this stopping theorem, we consider this symmetric random walk problem again. But we impose the initial condition that x0 is equal to k, and the stopping condition. So this process stops if xt is either 0 or a. So this is actually the stopping condition for the gambler's ruin problem. That is, either the gambler gets ruined or his opponent gets ruined. Okay. So what is the expectation value of this stopping time? So since we give the condition for stopping, the quantity of interest is the expectation value of this stopping time, t. So from a previous example, we know that this quantity yn, which is defined as xn squared minus n, is a martingale with respect to xn. Okay, so by the stopping theorem, we have the expectation value of yt. Okay, this is the expectation of y at time t. This should be equal to the expectation value of y0. And by definition, this is x0 squared minus 0. But x0 is k. So we have expectation value of k squared, but k is just a constant, so it's k squared. On the other hand, we can calculate this quantity in a different way based on the definition. So that is xt squared minus t, and that is xt squared minus expectation value of t. So okay, this expectation is what we are interested in. Okay, the first term is given by, so since at time t the value of x is either 0 or a, okay, so this would be 0 times the probability that xt is equal to 0 plus a squared times probability that xt is equal to a, and minus expectation value of t. And from the gambler's ruin problem, we know that this probability is k over a. Okay, and this is of course 0. So from the previous calculation, the left hand side should be equal to k squared. Therefore, expectation value of the stopping time is, let's see, that's ak, and ak minus k squared. So this is it. And actually this is result we have got in the gambler's ruin problem.